Midst of showing existence of square roots, right? So the situation is we're given a bigger than 0, and then we're going to show there exists a unique S such that S bigger than 0 such that S squared equals A, right? If you don't have the S bigger than 0, then of course it's not true that it's unique, as you know. Okay, so what was the plan? The plan was to let A be equal to the set of all x bigger than 0 such that x squared is less than A. And we checked last time that this was non-empty and bounded above. And so then we let S be equal to the sup of A. And then the idea is then to exclude S squared less than A and S squared bigger than A. And then you're done by the trichotomy. Yes?
What does that say up top under S greater than 0?
Okay. Yeah, so clear that up a little bit. Such that, yeah. Okay, last time we worked on this one, and remember what the strategy was. The strategy was to, so this, call this number 1 and this number 2. So the strategy for number 1 was to show there exists some epsilon bigger than 0 such that S plus epsilon squared is less than A. Now that's probably not the first thing that you would have thought of if you were asked to prove this. And again, you're sort of looking at the wisdom of 100 years or something or more, 150 years of thinking about how to solve problems like this. And remember, the completeness axiom didn't even exist until the 19th century. And people just sort of supposed that all these things were existed in the real numbers. But having said that, this is the most important thing that you're going to learn from this. You already know the statement. You know that square roots exist, or you know it, right? But what's important are the techniques. So these kinds of things are techniques from, basically they show up in real analysis, but they also show up in everything in which real analysis is applied. So you see them in differential equations and various areas. You can even see them in topology, complex analysis, and so on. So the techniques are the most important thing to take away here, right? And the reason why this was the strategy, remember, because if S plus epsilon squared is less than A, what does that tell you about the number S plus epsilon? Where is it? Certainly positive, right? Because S is positive. S is actually bigger than 1, right? Oh yes, and we are also working on the case A bigger than 1 to make life easier. But why, where is this by definition?
Between 0 and 1.
Well, no, that may not be true.
It's greater than S squared.
Its square is less than A. Where does that mean it's located in terms of what we have up here? It's in big A, right? Big A is exactly all those positive numbers whose squares are less than A. Well, this number's square is less than A. So this tells us that S plus epsilon is an element of A, right? That's just the definition of A. And what's the problem here, right? The goal is to get a contradiction. We're trying to exclude this case. Why is that a contradiction? Yeah, S is the sup and epsilon is positive. So that means that this is something that's in A, but it's bigger than the sup. Okay, so that violates actually which of the two conditions of the sup?
The second. A2.
First one, S1 or A, right? Because this is saying that S can't be an upper bound, right? So this violates S1 or A1, depending on which, right? They're the same thing, but depending on which set you're looking at. The other direction is actually going to violate A2, right? So this is a contradiction since S plus epsilon is greater than S, which is sup of A. So that contradicts A1, that the sup is supposed to be an upper bound. Okay, does everybody understand? I won't go through the calculation here again because we've got another one to do, and now we're going to do the S minus epsilon one, right? But does everybody understand why this is a contradiction? I mean, yes. Oh, okay. I mean, actually, we're just doing pre-calculus, right? Here, and in the next section, we're going to be doing absolute values. But that doesn't mean that it's easy pre-calculus, right? Okay, but does everybody understand why this is a contradiction now? So we know that this is not possible, okay? Because if this is true, we can nudge it and make it a little bit bigger and still have that true. So S can't be the sup. Okay? So let's now consider the case S squared bigger than A. Now, if we think about what we did here, right? We suppose this was true, and then we showed that we can nudge it a little bit, make it a little bit bigger, and have this still true, but you can't do that to the sup, right? You can't make the sup bigger and then still have something that's in the set. So that's why we got our contradiction here, right? And that contradicted A1. Now, in this case, we're going to show there exists some epsilon bigger than 0 such that S minus epsilon squared is still bigger than A. Okay, so again, the idea is that if S squared is bigger than A, then we can nudge it downward a little bit and still make the square bigger than A. Now, why is this going to be a contradiction again, if we can find this epsilon? We'll worry about finding epsilon in a bit, but let's try to see why this is going to be a contradiction. And taking a hint from what I said before, this ought to somehow violate A2, but this should look very familiar from A2, right? Okay, so then by A2, there exists what?
By A2, for every epsilon greater than 0, there exists some A.
Let's call it X because we're already using A, right? So
some X in A such that X is greater than S minus epsilon. A greater than
sorry, X is greater than, okay, all right, so we got to make sure we translate all our letters here, okay? And that's why it's good to not remember exactly what the letters are, right? Because, okay, it doesn't, all right. So there exists some X such that,
for every epsilon greater than 0.
yes, so, but we have this particular epsilon, so since it's true, right, when something is true for every epsilon, if I find any epsilon and hand it to you, the statement has got to be true. So I've got my epsilon. You're absolutely right, whoever said that I wasn't facing that way, but you're absolutely right that the original statement is that it's true for every epsilon, and that's important. It's not for some epsilon, it's for every epsilon. And once it's for every epsilon, anyone I pick up, and in particular this guy that I'm going to show I can find, has to work. Okay? Now, what would we like to do now? Well, so then we get X squared bigger than S minus epsilon squared bigger than A. And why is that a contradiction?
Because the set we're given?
Where is X? In A. And if it's in A, what's supposed to be true? Okay, there is a, okay, let me answer your question in 1 second, okay? If If there's something that you don't like up here, that's good, because there is something you shouldn't like up here. But anyway, does everybody understand this statement at least is a contradiction? Okay? So, question?
Would x have to be bigger than 1 for that to work out as well?
Well, x is in A. Okay, well, I mean, I think which part work out? I mean, if you suspect something here, that's good, because something is not right. And the reason I'm doing it this way is because this is a mistake that maybe half of you will make before this class is over. You will make it either in terms of this or in terms of absolute value. And if you're not seeing it now, then I'm hoping when you do see it, then it won't be you who makes a mistake. But I still predict about half in the homework, and well, hopefully not on the test, but that will probably happen too. Okay, what's the mistake here? It's kind of close, but the mistake is below this line. Okay.
Is that we automatically assume that x squared is greater than this?
Okay. Is it true that a bigger than b implies a squared bigger than b squared? Okay, if you say no, tell me a counterexample.
If they're both above 1.
Well, I don't think 1's the important thing here.
1/2 would be greater than 1/3.
No?
He's a big negative.
Yeah.
Then
Okay,
big positive.
so let's let b be equal to -1 and a be equal to, half. Okay? And b squared equals 1 and a squared equals 1/4. It reverses. So what if you were going to try to prove this? What would you want? What are you doing to get from here to here? You're multiplying the left by a and you're multiplying the right by b. When is that going to preserve the inequality according to some exercises you had previously? Things you proved about this.
When A and B are both positive.
If they're both positive, you're good.
So we would have to know x is greater than epsilon.
Yes, exactly. Okay? For this, we need epsilon less than s. I'm going to write it that way because, yes, I'm writing it that way because, remember, we're trying to pick epsilon small. Okay, so we're just going to hold on to this, and when we finish our calculation, we're going to throw this into the mix. But does everybody see why you need this? Because if you don't have this, if epsilon were something gigantic, then you would still get this. But this is some very, very negative number, and when you square it, it just blows up. And you can't expect this to be true anymore. Okay? I repeat, about half of you will make this mistake. And each time I get more forceful about saying this, hoping that the proportion will diminish, okay? But there's a similar mistake with absolute values, and we're going to do absolute values in the next section. It's also not true for exactly the same kind of reason. Does not imply, always anyway, absolute value of A is less than absolute value of B. And actually, some of you probably made this same mistake in calculus. It happens a lot when you're doing max-min theorems and things, right? And okay, so don't make this mistake. It's very basic, but you just have to be careful. Okay? So we need this thing here. Now we're going to do basically what we did last time at the end of class, and we're going to expand and we're going to make sure our logic goes in the right direction. Okay, so what we want is this. So let's do our calculation. We want s minus epsilon squared bigger than a. And again, I'm doing a parallel argument now just to get my answer. But to emphasize, if you do this, it is exceedingly dangerous. It's useful, but when you are done, to make sure you haven't made a mistake, do what I did last time and what I'm going to do now. When you're finished, write out one long inequality so you can make sure that every single one of the inequalities goes in the same direction. Remember, I'm starting with what I want. If I end up with something true, that doesn't prove anything unless my logic goes uphill. And that's very important to think about, just like last time, as we think about how we're going to manipulate this. And with inequalities, manipulation is possible because you have wiggle room. Okay? You always have some wiggle, well, not always, but usually you have a little wiggle room, right? So, and I'm not going to put any arrows yet, right? S squared minus 2s epsilon plus epsilon squared bigger than a. Okay, now I'm going to put an arrow, right? Remember, our logic is going this way. We're trying to get what's at the top. Now, just like last time, I have a quadratic in epsilon. So I'm not going to be able to solve for epsilon, because if I solve for epsilon, I need to know about square roots of things, and that's exactly what I'm trying to prove. So once again, the irritant, if you want to call it, is this guy right here. Now last time, we replaced epsilon squared by epsilon. What did that require about epsilon?
Epsilon greater than.
We wanted epsilon to be less than 1, right? And why did we want that? Because when you squared epsilon, it gets smaller. And last time, we had this going on. And so we wanted to make sure that this one was bigger than that one. Because if this was bigger than that one, if this inequality